All right, I'm back for more review problems. Okay, so number 2 and number 3 kind of are linked up, so I wanted to make sure I get those on the same video. So number 2, I gave you two functions. The first one's a little bit goofier than the second one, actually. So I gave you two different functions, and for each function, I asked you to find the interval over which the function is increasing or decreasing. So this is skill number 2. We're finding intervals over which a function is increasing or decreasing. So when you do this, you are going to still find your critical numbers. And you use those critical numbers to make intervals. And then you are going to choose a test value within each interval. And if the derivative, the value for the derivative is positive in that test interval, then we would say it's increasing. And if it's negative in that interval, we'd say it's decreasing. Again, you should have all these steps in front of you on the guided notes. But let's go through that process. Okay, so here's my function, x squared divided by x squared minus 9. So first I want to find the critical numbers. I can right away see that 3 is going to be a little bit of a goofy spot. Positive or negative 3, because at that point this whole function is undefined. So that kind of makes it a critical number or a point I need to look at. But let's go through the process. So we're going to take the first derivative. So when I took the first derivative, I used the quotient rule. So I did low d high, x squared minus 9 times 2x d high minus high d low divided by low. And that simplifies. So this gives me 2x cubed minus 18x minus 2x cubed over x squared minus 9 squared. Clearly we can lose these things. So I end up with negative 18x over x squared minus 9 squared. Okay. So critical number, when x is equal to 0, this is 0. Right? But again, we have this point where it becomes undefined at negative 3 and plus 3. So I have to look at that as well. Okay, so I can't take the derivative at these points, which makes them a critical number. And again here, just because if you plug that in, you get a 0. So I use my critical numbers to develop my intervals. So I'm going to go negative infinity to 0. Or I'm sorry, to negative 3. Let's take them in order, for heaven's sakes. So negative infinity to negative 3 is one interval. Negative 3 to 0 is the next interval. That's the next point of interest. Positive 3 is my next point. And then I take that all the way up to infinity. I'm running out of room, sorry. 3x infinity. Sorry, let's make a line to kind of. Okay, so here are my intervals. Negative infinity all the way up to negative 3, negative 3 to 0, 0 to 3, 3 to infinity. So I use those critical points to build my intervals. Then you pick a test point in each interval. It really doesn't matter what it is. I always go for easy numbers. I did negative 4, negative 1, positive 1, and 4. Okay, so it doesn't matter. As long as they're in the interval, you pick a value. And then you take that value and you plug it into your derivative. So I'm plugging it into this. If you end up with a positive number, that means my derivative, my slope is positive. This is increasing here. If you end up with a negative number, that means my slope is negative. I'm decreasing here. So I just plug and chug. When I plug negative 4 into here, I get a value that is greater than 0. When I plug negative 1 in here, I get a value that is also greater than 0. When I plug positive 1 in, I get a value that's less than 0. And when I plug 4 in, I get a value that's less than 0. So what does this mean? It means I'm increasing on the intervals negative infinity to 3 and then 3 to 0. Now you can't say negative infinity up to 0 because remember that I should say negative 3 for the love, sorry. You can't say negative infinity up to negative 3 because remember that at this value the thing is totally undefined. So you have to go I think I said what I wanted to wrong. Let me restate that. I'm not going to remake this video. I can't say the interval is negative infinity up to 0. I have to split it by this -3, because at -3 the function is totally undefined. So it's increasing on this interval, and then it is decreasing essentially from 0 on up, but again at 3 it's undefined, so we have to write it as 0 to 3, and then from 3 up to infinity. Okay, so that's how we find our values, where it's increasing or decreasing. The next function is a lot more cut and dry. So the next function, we're going to go through the same process. It's a little bit quicker. So first we find our critical points. So I'm going to take the derivative of the function. This one I'm just using the power rule. So it's -4x plus 4 is my derivative. And we set it 0 to find the critical points. There's no point, if you look at this function, there's no place where it's undefined, so that's nice. So just, where's the first derivative equal to 0? And it is when x is equal to 1. So we have one critical point. So then we use our critical points to come up with our intervals. So the intervals will be -infinity to 1, and then 1 up to +infinity. So much shorter. Then we choose a test value within each interval. So here 0 is a nice easy one. And then here, what did I do? 2? Yeah. We plug our test value into the derivative. So I'm plugging it in here. Again, if it is positive, I have an increasing interval. If it's negative, I have a decreasing. So when I plug 0 in, I get a positive number, as you can see. And when I plug 2 in, I get a negative number. So this means that I am increasing. This function is increasing on the interval -infinity to 1, and it is decreasing on the interval 1 to infinity. And that's it. So every time we're looking to find those intervals where something is increasing or decreasing, that means we're looking at first derivatives. When we're in the future looking at intervals where we have concavity, that's second derivatives. So intervals where something is increasing or decreasing, we want to go look at that first derivative, and we want to figure out, is the first derivative positive or negative in each intervals. Again, we use our critical points to identify what those intervals are. Okay, so that's kind of the big picture. Now, number 3, I just asked you for these same functions to find our maximum and minimum values. And so to find the maximum and minimum values, if you already have all of this worked out, like you already have your first derivative and you've found your critical points, the easiest way to find your maximum and minimum values is to use the first derivative test. The other way you can, and we could for these, I'm not going to, but you can use the second derivative test as well. So since we already have first derivatives here, let's go do the first derivative test. So I'm doing number 3, like just right here. So the first derivative test says I want to look at my critical points. Again, I've got them all defined. And I want to look at, at a critical point, does my first derivative go from positive to negative or negative to positive? If it does neither, then it's not a max or min. So here, I'm going from, so if I'm greater than 0, this is positive, greater than 0, positive, less than 0, negative, less than 0, negative. I always write it, like that's just an easy visual for me. Okay, so here, I'm going from positive to positive. I'm not changing signs at all, that's nothing. It's not a maximum, not a minimum, just keeps increasing. It's really goofy. If you actually look at the graph for this one, it's kind of goofy what it looks like, but the slope is increasing this whole way. Now, right here at this point 0, I go from positive to negative. The first derivative test would say when my slope goes from positive to negative, I have a maximum value. That's where I've peaked. So we say, okay, I have a maximum value at 0, and then you can plug in whatever that is to give you my max. It's actually 0, 0 is what it is if you plug and chug. Okay, so my maximum value occurs here where I go from positive to negative. Then I go from negative to negative. It's staying the same, so it doesn't change. So I have a maximum. I don't have a minimum value. Again, if you graph this, you will see. It kind of looks like a, ooh, I threw my marker. Looks like a parabola. So you've got the max up at the apex of the parabola, but then it just keeps decreasing forever. So there's no defined minimum. So there's my maximum value, first derivative test. Let's go do the first derivative test here. So the first derivative is positive on this interval, negative on this interval. Again, I have one spot at point 1 where I go from positive to negative, so that is a maximum as well. So we would say my maximum value is at 1, and if I plug 1 in, I can figure out what that is. Let's see, negative 2 plus 4 is 2 plus 3 is at 5, I think. Asterisk that because I'm going out of my head. So this is my maximum value. Again, for this function, I don't have a defined minimum doing the first derivative test. So that's, in a nutshell, finding intervals over which something is increasing or decreasing, and finding maximum and minimum values of open intervals. So to find those maximum and minimum values, we just look at where's the first derivative changing from positive to negative or from negative to positive. Always will be at a critical point. So we just look at those critical points. I'll come back in the last problem. I'm going to keep doing it on this PowerPoint, but I mean this video. But in the last problem, I'll look at first derivative test and second, so you can see me do both at once. Okay, so let's do the last problem. I picked some easier ones to differentiate, so it should make it quicker. The last problem, we're going to practice with that final skill, which is intervals of concavity, and then we'll come back to these max-min values too. Okay, so the last problem, I have to look at it and find it. I gave you two functions again. So this is problem number 4. And the first function was f of x is equal to 3x squared minus x cubed. And the second function we'll end up doing over here was 1/2 x to the 4th plus 2x cubed. Okay, so in number 4, for both of these functions, I asked you to find the intervals in which it's concave upwards or downwards, and then I asked you to find the maximum and minimum values for the function. So let's start with the concavity. I'm going to do the concavity for this one. So if I want to find the intervals of concavity, these are places where the slope is either increasing or decreasing. So we are looking at where is the second derivative positive, that's where the slope is increasing, or where is the second derivative negative, that's where it's decreasing. So to find our intervals of concavity, first we need to find our points of inflection. We kind of do the same process we just did, but instead of doing it with critical points, we do it with points of inflection. So points of inflection are places where the second derivative is 0 or undefined. So we have to find our second derivative. So the first derivative of this function is, let's see, 6x minus 3x squared. And then the second derivative of this function is, what is it? I'm trying to, is 6 minus 6x. Okay. So we want to find where is this? 6 minus 6x equal to 0. That gives me my point of inflection. And that happens when x is equal to 1. So my point of inflection is 1. And what we do is we build intervals with our points of inflection, just like we did with the critical points in the last problem. So I'm going to go negative infinity is less than x is less than 1. 1 is less than x is less than infinity. And that's it. So you find, or you choose, you don't find, you choose a test value in each interval. So here I would choose test value of 0, and here I'll choose test value of 2. And you plug that value in to your second derivative. If your second derivative is positive, that's concave up interval. If it's negative, it's concave down interval. So here, I'm going to plug in 0 into my second derivative, and that gives me 6. So it's a number that's greater than 0. It's positive. Here, I'll plug in 2 to my second derivative. And if I plug in 2, I get negative 6. So that's less than 0 or a negative value. So we would say we are concave upwards on the interval negative infinity to 1. And we are concave downward on the interval 1 to infinity. Okay, now I'm going to skip finding the maximum and minimum values for a second, and I'll come back to that. But that's how we find concavity. So let's go over and do the same exact thing here. So we take our first derivative. The first derivative is equal to 2x cubed plus 6x squared. And then we find our second derivative. So this would be 6x squared plus 12x. And we want to look at where is that second derivative 0. So I'm going to factor out a 6x. So I'm going to say 6x times x plus 2 is equal to 0. So where is this 0? It's 0 when x is equal to 0 or negative 2. So those are my 2 points of inflection. So again, we make our intervals, but this time instead of making them with critical numbers, we make them with our points of inflection, just like we did over here. So I'm going to say negative infinity to negative 2, and then negative 2 up to 0, and then 0 up to positive infinity. So here are my intervals. I choose a test point in each interval. So here I chose a test point of negative 3. Here I chose negative 1. Here I chose positive 1. And I'm going to plug each of those test points into this second derivative to find if my second derivative is positive or negative. So when I plug in negative 3 to my second derivative, I got a number greater than 0. When I plugged in negative 1, I got a number less than 0. And when I plugged in 1, I got a number greater than 0. So this means that I am concave upward, let's see, from negative infinity up to negative 2, and then from 0 up to infinity. And then I'm concave downward from negative 2 to 0. Okay, so that is how, for really any kind of function, we can determine our intervals of concavity. So just a review of that skill. You find your point of inflection, you use your points of inflection to build intervals, make a test point, plug the test point into the second derivative. So really finding intervals where we're increasing or decreasing, you're doing that with first derivatives. You're finding your critical numbers, you're making intervals, choosing test numbers, and plugging them into your first derivative function. Here, we do all that with a second derivative. So we find our points of inflection, make intervals with points of inflection, choose test values in the intervals, and plug that into our second derivative function. So those two things, really, those processes are very similar to each other. So just make sure you're careful in your head, like, okay, am I looking for intervals of concavity or just where the function is increasing or decreasing? One, use the first derivative, the other, use the second derivative. Now, what about finding those absolute or relative maximum and minimum values? So you can use to find minimum and maximum values. You can use the first derivative test, or you can use the second derivative test. On these two, I'm going to use the second derivative test because I've kind of got it set up here. But then I'm going to come back and use the first derivative test to prove my point on one of them. Okay. So, so for the first function, if we do the second derivative test, the second derivative test has you find the critical numbers. So that's what the first derivative has you find the critical numbers and then the value of the second derivative at the critical numbers. Okay. So my first derivative is 6x minus 3x squared. If I factor this out, this becomes 3x times 2 minus x, and my critical numbers end up being 0 and 2, okay? So you plug in the critical numbers into your second derivative. So I'm going to plug in 0, and when I plug in 0, I end up getting 6, and you plug in 2, I end up getting negative 6. Since it is greater than 0 here, this is a minimum value. whenever I get a number of second derivatives greater than 0 on the second derivative test, that tells me this is a minimum value. And this is a maximum value. So at the point 0, I have a minimum. And at the point 2, if you plug in and see what that value ends up being, I have a maximum. So that's using the second derivative test. I can come over here and do the same thing with this function. So my first derivative is 2x cubed plus 6x squared. So I'm trying to cheat and find where I found my critical numbers. If I factor out, I can factor out a 2x squared. This becomes x plus 3. My critical numbers end up being 0 and negative 3. So if I take the second derivative of 0, or plug in the second derivative of 0, I get 0, actually. And if I plug in negative 3, I get 18. Okay, when you get 0, this means I have neither a maximum or a minimum at this point. It's neither one. Here I get 18. This indicates a minimum because it's a positive value. Let's redo this one, because I'm going to erase what's on the left, I think. Let's redo that one using the first derivative test, just so you can see that we end up with the same thing. Okay, so I'm going to look at function b, and I already correctly found using the second derivative test that my critical numbers were 0 and negative 3. And when I plug in those values to my second derivatives, I get a minimum at negative 3. I have no maximum. Let's look at it with the first derivative test. Okay, so again, I said my critical numbers were 0 and negative 3. I can use that to build intervals. So I can say, this is intervals for the first derivative. So negative infinity up to negative 3, then negative 3 up to 0. Whoops. And then 0 up to infinity. So if I choose a test value in each of those intervals, here I'm going to choose negative 4, here I'm going to choose negative 1, here I'm going to choose 1. If I plug in these values to my first derivative function, because I'm using the first derivative rule, this is my first derivative function, okay? So if I plug these values in here, my first derivative ends up being negative. Here, my first derivative ends up being positive. Here, my first derivative ends up being positive. So I'm going from negative to positive at the point negative 3, which it would indicate a minimum at the point negative 3. Here, I go from positive to positive. So I have a minimum point, I have no maximum. It just keeps increasing, which is exactly what the second derivative test showed us. It gave us the same thing. It shows this negative 3 is a point where we have a minimum. So it's just a, you can do it either way. In this case where you're already dealing with concavity, you've got the second derivative solved out right in front of you. So the second derivative test is a little bit quicker. So it tends to be that the first derivative test is quicker when you're finding intervals where something is increasing or decreasing, and the second derivative test is quicker when you're finding intervals for concavity, but really both are totally correct. And if there's one you're more comfortable with, or if you want to use one to check yourself with the other, by all means do it. And that's the end of our review.